So in the last class, we have seen the 5 properties of great orthogonality theorem. Let us now try to see how to apply these properties. So now we'll see application of GOT rules or properties to develop character table. So at this point, I will mention that the character table is a complete set of, I'll write complete set of irreducible representations of that particular point group, and then many more things will deal with that, what all character table include. But basic thing is that it should have the complete set of IR representations. So now let us see by taking example how to use this great orthogonality theorem rules to actually develop all the IR representations without doing any symmetry transformations, okay, or symmetry operations. So let's take an example of our favorite molecule, which is water, because we have been dealing with that. So we know all the irreducible representations already. So C2Z, sigma V1, sigma V2. As I said, I will not even worry about what my basis sets are. So I will just start from the basic rules. So one of the properties says that the number of IR representations is equal to number of classes, right? So this property tells me that there are 4 classes. So this property tells me that there has to be 4 irreducible representations. So I will just write tau 1, tau 2, tau 3, tau 4. So at least I know that there has to be only 4 and not more, not less, and it has to be only 4 irreducible representations. So now we have to find out these 4 representations using this. Okay. So now another rule, which is I think the property 1, which we said, which says the sum of squares of dimensions of IR representations is equal to H, right? So what does it mean? So we have 4 representations. So that means each one has an associated dimension. Let's call these dimensions as L1, L2, L3, L4. So now sum of the squares of these dimensions, that is L1 square plus L2 square plus L3 square plus L4 square is equal to H. H is the order of the group, which is 4 here, right? Now, what are the options or what are the possible solutions for this? So the only possible solution for this particular equation, so we have to use hit and trial. There are 4 variables and only 1 equation. So there is no other possibility to solve but by doing hit and trial. So what does the hit and trial say? The only possible solution is if we do 1 square plus 1 square plus 1 square plus 1 square, right? Now you can say that it can also take negative as the values, right? So it can take the negative values, but because these are dimensions, so dimensions cannot be negative. So it has to take only positive values, right? So dimensions cannot be negative, right? So it has to take positive values only. And we also know that the character under E represents the dimension. Why do we say that? So let's say if we are applying E on a unit vector, then I will get a matrix for 1 cross 1 matrix, right? If I'm doing E operation on basis set which has X and Y, I will get a 2 cross 2 matrix, right? So in this case, if I'm getting 1 cross 1 matrix, the dimension is 1. If I'm getting 2 cross 2 matrix, the trace is 2 and that is the dimension. If I'm having a basis set as X, Y, Z, that is 3 basis sets. So I will get 3 cross 3 identity matrix for which the trace will be equal to 3 and the dimension will also be equal to 3. So that means the trace under the operation E represents the dimension. So now we know that all the dimensions are 1, 1, 1, 1. So we can write the trace under E as 1, 1, 1, 1, right? So from 16 unknown elements, we have solved for 4 in one shot, right? So I hope that is clear. So again, I'm saying sum of squares of dimensions of an IR representation is equal to H, which gives me L1 square plus L2 square plus L3 square plus L4 square equal to 4. The only solution is 1, 1, 1, 1, because we cannot take negative values because these are dimensions. And as we know that the dimensions are nothing but the trace of matrix under E, so we can safely write 1, 1, 1, 1 here, right? So you can write it as a matrix or as a trace. Now, because it's a one-dimensional representation, so it does not matter whether you are writing it as a trace or a matrix, but in this case, we are actually determining only trace. Okay. Now for next property. So next property tells me, which is the property 3. Okay, rule property 2 actually, which tells me that summation over all R for chi I R and the square is equal to H. That is, the sum of square of character over all operations will be equal to H. So this again gives me a value. So let's call it as, let's call these as maybe we already know this. So A, B, and C. Okay. So this tells me that 1 square plus A square plus B square plus C square equal to 4. Now you don't have criteria that it cannot be negative. So now ABC can be positive or negative. Okay. So 1 we already know. So now ABC can take all the positive values. All 3 can be positive, all 3 can be negative, and so on, right? Or 2 can be positive, or 1 can be positive. Or let's see what are the possible solutions here. So let's consider the first solution as A equal to B equal to C equal to 1. That is a valid solution. So we can populate this table as, so let me remove this and write down this as 1, 1, 1, right? Now let's say that, let me write ABC over here now. So now we need to solve for this. Now there is a condition which also tells me that tau 1 has to be, tau 1 and tau 2 are orthogonal, right? That means the product of these, this product plus this product plus this product plus this product equal to 0, right? So now we know that 1 into 1 plus 1 into A plus 1 into B plus 1 into C equal to 0. Now what are the options to solve this equation now again? And we know that 1 square plus A square plus B square plus C square also. So now we have 3 unknowns and 2 equations. A square plus B square. This condition still holds, right? This is the orthogonality condition, and this is the condition where I said that the sum of the square of characters should be equal to order of the group. Okay. So solving this, how do we solve this? So this particular tells me that A, B, C can take the values as plus minus 1, right? Nothing else is possible. But this one restricts the values. How does it restrict? That 2 of the summations or 2 of the products have to be positive, 2 of them have to be negative, so that the product is equal to 0. So sorry, this one is not 0. This one is 4, right? Okay. So this tells me, this implies that if A is positive, B will be negative and C will be negative. I can say that A is negative, then B is positive, plus 1, and C is minus 1, right? I can say that these are the possible 3 solutions. B is negative and C is positive. no other solution is possible. So you can try this out, which will satisfy all these three solutions, will satisfy these two equations, right? So this implies that I can populate this table as 1 minus 1 minus 1 minus 1 minus 1 1 minus 1 1 minus 1. And now you must appreciate this fact that when we did unit vector transformations, we got this particular character table while doing symmetry operations and looking at its effect onto x, y, z and rx, ry, rz, right? So here we have not done any of these operations, or we have not considered the basis set, we have not considered the molecule also. We have just worried about the solutions of this using the rules or properties of great orthogonality theorem. Okay, so I hope this is clear. So now let's take another example so that it goes into heads nicely. Consider C3V. We have seen this example also. So C3V has E, C3 and sigma V. So now that we are dealing with trace, so we will only use one of the class elements and we will not bother about rest of the class elements because the traces are same. Okay. Okay. So now, first of all, how many representations are possible? How many IR representations are possible here? So number of classes are 3, right? So that means number of irreducible representations are also 3. That is defined by the number of classes, because you have 1, 2 and 3 classes. So that means you have tau 1, tau 2, tau 3. Okay. Now let us go to the first rule, which says that L1 square plus L2 square plus L3 square, the sum of square of dimensions is equal to H, right? What is H here? The order of the group is 6, right? So now what are the options? L has to be positive. It cannot go negative. So that is one of the conditions. So now by using hit and trial, again, we have to resort to hit and trial because we have 3 variables and only one equation to solve. So the only option this equation will give you for positive numbers, that L1 will be equal to 1, L2 will be equal to 1 and L3 will be equal to 2. So 1 square plus 1 square plus 2 square will give you 6, right? So now let us go back and fill this up. So 1, 1 and 2, right? Now let us write this as A and B and see how do we solve this. So now we also know that summation over all R, sum of squares of characters over all R is equal to H, which tells me that 1 square plus A square plus B square is equal to 6, right? So we already know this is 1. So the important thing which is not to be missed is that you also have to multiply here, because we are only dealing with traces here. So you also have to multiply with the class size here, right? So class size goes here. So what is the class size here? Class size is 2 here and 3 here, right? So we are multiplying with class size because we have to take summation over all R. And if we are doing only 1 square plus A square plus B square, we are doing this is under E, this is under C3, this is under sigma V1. So we have not considered for C3 square and sigma V2 and sigma V3. So we have to multiply this. So 1 square plus 2 into A square plus 3 into B square will be equal to 6. Now again, what are the possible solutions? A and B can be positive or negative. Let's consider the first solution where A is equal to 1 and B is equal to 1. So this satisfies the condition. So you have 1 plus 2 plus 3 equal to 6, right? So that means we can fill over here, fill the table as 1 and 1. Okay, so that is easy. So now let us write down A, B and C, D again. Okay, and apply the same conditions again. Now if we do, so 1 square plus 2A square, so again multiplying with the class size, plus 3B square is equal to 6, and the second equation is 1 dot 1 plus 2 into 1 dot A plus 3 into 1 dot B is equal to 0. Now this is the orthogonal condition, right? So what is the solution for this? If I do this, what will be my solution? So if I have this, I get 2A, 1 plus 2A plus 3B equal to 0. So now I have to find which number, which digit A and B both can take plus 1 and minus 1. We have seen that earlier. In this case, like if you put plus 1 also, it will take the values, but plus 1 values are already taken for tau 1. Now the negative 1 values, can it take both A and B can be negative or not? So let us test that. Let's say A is minus 1 and B is also minus 1. Does it follow this equation also? So that will give you 1 minus 2 minus 3, which is not equal to 0, right? So that means this is not a solution. So again, we are doing hit and trial because we don't need to do hit and trial here. So we can actually solve it properly because there are two variables and two equations. Okay. So now if we do A is equal to plus 1 and B is equal to minus 1, it does solve this, right? So you can see that this becomes plus 1 and now this becomes 1 plus 2A minus 3B, right? 1 plus 2 minus 3 will be equal to 0. So now we have found one more solution. So let's go back and fill this up. So 1 and minus 1. So now we have two variables and we can easily get two equations from two orthogonality conditions. So let's do that. So 1 into 2 plus 2 into 1 into C plus 3 into 1 into D should be equal to 0. Then 1 into 2 plus 2 into 1 into C minus 3 into 1 into D equal to 0. So here I have exploited tau 1, tau 3, and here I have exploited tau 2 dot tau 3 equal to 0, right? So now we have two equations, two variables. You can easily solve it, and you can see that C will come out to be minus 1 and D will come out to be 0 for this. Okay, so that means we have got this trace also. And remember, we are now getting the trace, not even the matrix elements, directly trace. So this is the complete character table, not complete, partial character table, which has complete set of IR representations. Why I'm not saying it's a complete? Because we still don't know what are the basis sets for this. We'll work it out later, but let's first see how to write down the IR representation. So we have successfully written down IR representations for C2V and C3V point groups without having to worry about what are the basis sets, what is the molecule, how do you operate C3 or how do you operate sigma V1 on to different operations. But by just following mathematical rules, we are able to write down the characters under irreducible representations. So in the next class, we will see how to go from reducible representation to irreducible representation. So far what we have done is we have used GOT to identify how to write irreducible representations alone. Now we will do reducible. We will go from reducible representation to irreducible representation, which is also important. So we'll discuss that in next class. Thank you.